Historically, quality management auditing relied on a simple equation. Fixed inputs reliably yield predictable outputs. This illustrates that baseline, a mechanical assembly line smoothly processing identical widgets. You set the parameters, and the machine repeats the exact same action. Traditional ISO 9001 audits are built entirely around monitoring and controlling these predictable, deterministic systems. But integrating artificial intelligence into a QMS disrupts this linear flow. Whether an organization uses predictive supply chain forecasting or computer vision for defect detection, the underlying mechanics of the process change. AI introduces non-determinism. The traditional linear flowchart of input, process, and output fragments into multiple probabilistic branching pathways, generating varying results. But the core objectives remain intact. The May 2026 ISO 9001 Auditing Practices Group guidelines clarify the audit must adapt to this architecture. Auditors can no longer rely on simply checking the final manufactured product. They must now evaluate the probabilistic engine itself. Successfully auditing an AI-integrated QMS requires moving away from attempting to review raw source code and shifting focus towards systemic governance. We can organize this governance into 3 strategic priorities. This architectural model outlines the new framework for ISO 9001 AI compliance, dividing the audit into input, process, and output. The first pillar evaluates data and secrecy, verifying the exact dependencies and raw inputs feeding the model. The second pillar targets transparency and oversight, assessing how the model explains its decisions and what human controls are active. The third pillar addresses performance and drift, monitoring the system for non-deterministic behavior and degrading outputs over time. Mastering these pillars provides a logical methodology to certify an AI tool within a QMS, ensuring the organization is not exposed to hidden algorithmic risks. We start with the input. An AI model is strictly bound by data dependency. It will only ever be as compliant, accurate, or unbiased as the data it trains on and processes. Consider a QMS using AI for supplier evaluation. The system ranks vendor performance by analyzing massive external datasets and running predictive models to calculate risk levels. Under ISO 9001 Clause 7, which covers support, auditors must investigate the training data. This data flow map shows raw external datasets feeding into a central supplier evaluation node. Auditors must verify the provenance, infrastructure, and document control at each of these incoming streams. Using external AI tools also introduces a severe secondary risk, the leakage of intellectual property. This requires a recalibration of Clause 4 regarding the context of the organization. Auditors must evaluate third-party vendor relationships to locate exactly where corporate data travels. The auditor must explicitly verify that proprietary QMS metrics, like internal defect rates or supplier pricing, are not inadvertently being siphoned off to train a public AI model. If the input data is structurally compromised, biased, or leaks corporate secrets, the entire QMS fails compliance before a single physical product is manufactured. Moving to the process logic, we confront the reality of complex algorithms like deep learning. This solid, glowing black cube on an inspection table represents the core issue. The internal decision-making logic of these systems is completely obscured. This creates a severe challenge for explainability. When an AI model flags a specific anomaly, an auditor often cannot trace the exact mathematical reason why that decision was made. This direct conflict with Clause 8, operations, becomes obvious in systems like automated defect detection, where computer vision independently accepts or rejects parts on a production line. Because the math is opaque, the audit must focus on operational safety nets. In this decision tree flowchart, a critical path is blocked by an automated decision. Auditors must verify that human-in-the-loop protocols, like a mandatory human override, are active before any critical automated decision is finalized. This ties directly back into Clause 6, planning. The auditor must look for documented risk assessments that explicitly account for algorithmic bias and system errors. Organizations must have clear, actionable fallback protocols and emergency plans ready to deploy if the automated system fails or begins hallucinating data. An auditor may never possess the ability to validate the AI's internal mathematical weights, but they maintain absolute authority to audit the human oversight built around that system. Finally, we examine the output logic. Because AI is non-deterministic, A model that operates perfectly today may degrade tomorrow, even if its underlying codebase remains entirely unchanged. This degradation is known as model drift. This time-lapse illustrates the concept. Just as elements warp a physical blueprint, external factors degrade digital integrity. In AI, model drift occurs when the system loses accuracy because the external, real-world variables and contextual data it relies on have shifted. Because of drift, traditional spot checks no longer satisfy Clause 9, performance evaluation. This line graph shows accuracy holding steady before drifting into a non-compliant zone. Clause 9 mandates continuous statistical monitoring over time to catch this behavior. This continuous monitoring forms a direct link into Clause 10, improvement. When AI outputs generate nonconformities, it must trigger an immediate root cause analysis. That analysis must feed directly back into parameter adjustments and model retraining to stabilize the system. Maintaining systemic conformity depends on an infinite loop of measuring drift and enforcing model retraining. To summarize, the modern auditor's objective has shifted. The job is now to verify data architecture, ensure algorithmic transparency, and mandate continuous model performance. Executing these three strategies requires a specific expansion of the auditor's own skill set. This Venn diagram outlines the new competencies. First, auditors need foundational AI concepts paired with data literacy. Next, they require digital risk awareness and a firm grasp of ethical and legal privacy considerations. Operating at the intersection of these disciplines defines the modern QMS auditor. Overlapping these skills empowers an auditor to ask the exact right questions regarding intellectual property protection, algorithmic bias, and non-deterministic behavior. Over the next decade, AI will become an invisible, ubiquitous layer within all quality management systems. Artificial intelligence offers massive computational speed and predictive power to the enterprise. But true quality assurance will depend entirely on human auditors who apply specific logic to systems that cannot explain their own internal reasoning.